Dear Chairman, thank you very much for your kind introduction and thank you very much for having me again this year. I am Matthias Arnold, the CTO of the LETS OPC UA Companion Specification. LETS is an acronym for Laboratory and Analytical Device Standard. In the next 50 minutes, I provide you with an overview of the upcoming LETS OPC UA specification for the laboratory and analytical domain. We will start with an introduction and update on the current status of LETS OPC UA. Then I will show you a proven workflow for implementing LETS OPC UA in your instrument and provide an overview on the various instrument types that we've successfully modeled or even implemented using LETS OPC UA. Finally, I will explain how you can harness the power of LETS OPC UA in laboratory automation. By leveraging the robust OPC UA ecosystem, we can enable seamless, teaching-free integration between instruments and robots. What are we trying to achieve with LETS OPC UA? We aim for true plug-and-play integration of laboratory and analytical devices along the laboratory workflow, seamless connectivity of devices with an absolute minimum of configuration, if any, covering use cases such as monitoring and control, workflow orchestration, and asset management. We are aware that it is hard to get this right. Just imagine the large number of different instrument types that need to be considered. We all know that achieving connectivity in our domain is challenging. Establishing plug-and-play interoperability between various lab analytical devices on one side and diverse applications like SCADA, LIMS, ELN, data, asset or service management on the other side is no easy task. As you know, the team behind the LETS OPC UA joint work group is on a mission to tackle some of these obstacles. We developed an OPC UA based communication protocol that targets essential and common use cases in the laboratory and analytical domain. Let's break down the use cases we are targeting. First, remote monitoring, alarms and notifications. This is the starting point because understanding what's happening is crucial for making decisions and taking action. With remote monitoring, you can keep an eye on the status. Additionally, remote control allows you to start or stop functions, adjust parameters and more. These monitoring and control capabilities lay the foundation for automation. Second, program management and orchestration. You can list program templates, select and execute programs, monitor their progress, and handle result data generated by devices, especially analyzers. These use cases are essential for orchestrating instruments along workflows. Third, asset management use cases, covering condition monitoring, maintenance, service, calibration, validation, and many more. These use cases are vital for enhancing serviceability and ensuring efficient asset management. In a nutshell, LETS supports automation, orchestration, service and asset management use cases. By addressing these critical aspects, we aim to optimize and streamline laboratory processes. But how can we achieve plug-and-play interoperability for such a wide variety of instrument types with vastly different levels of complexity. We achieve this by offering a generic toolbox of standardized building blocks that represent the functionality and capabilities of laboratory and analytical equipment. Alongside, we provide building rules that define how these blocks can be combined and arranged. Now, let's take a closer look at some of these building blocks, focusing on their specific use cases. The building blocks within the category called functions play a crucial role in the use cases of remote monitoring and control. With these blocks, remote clients can effortlessly explore and utilize all the device's functions, such as sensors, controllers, timers, covers, and more. Furthermore, accessing essential metadata like name, description, status, data type, ranges, engine units, and more becomes a breeze. In addition, associate event logs, such as for audit trails and data histories, are available. The best part is that all of this is achieved in a plug-and-play manner, without the need for any prior configuration. The building blocks related to program and result management are vital for remote orchestration use cases. These blocks enable remote clients to effortlessly list, upload, and download program templates stored on the device. Moreover, they allow launching program runs based on specific templates and provide all necessary contextual information such as associated job, associated task, list of samples, parameters, and so on. While a program is running, you can easily monitor its status and progress. Finally, accessing the results of a run, including context information, endpoints, files, and more, is made seamless. And, as before, all of this is plug and play without the need for any configuration. The building blocks for use cases related to asset management and service leverage existing and well-established OPC UA companion specifications, including devices, asset management basics, and machinery basics. This approach ensures that laboratory and analytical equipment can be cross-industry compatible for those specific use cases. I think this is a very valuable feature to have. Using these building blocks, remote clients can effortlessly explore aspects of a device and its components, including nameplates, condition monitoring variables, and health status. Furthermore, they can access the location of devices and the status of recurring tasks such as service, maintenance, validation, calibration, cleaning, and more. As mentioned before, all of this is based on industrial interoperability standards, ensuring seamless communication and compatibility. People often inquire about the suitability of the Let's OPC UA specification for various instrument types, applications, and use cases. They ask if there are any integrations available, whether as prototype or close to release. Additionally, they wonder how challenging it is to integrate Let's OPC UA and if there are any tools or examples to assist with the process. During the next few minutes, we'll address these questions. The results and findings we'll present were primarily generated during our hackathons and workshops. These events provide real-world testing and validation of the concepts and specifications in an agile manner. At this moment, I'm attending the 5th edition of the Let's Hackathon hosted by Agilent in Germany. Let's kick things off with an overview of the different instrument types we've modeled using Let's OPC UA. As mentioned, most of the information models were created and in some cases implemented in real-world devices during our workshops and hackathons. Let's start with some analytical instruments. On the left picture you can see an integrated HPLC system from Agilent. During the last hackathon we successfully created a Let's OPC UA information model for one of their HPLC systems, and the colleagues from Agilent implemented it in their HPLC system simulator software. This early prototype serves as a starting point for the ongoing work of the ASI/CAISY OPC UA working group. This group focuses on integrating analytical instrument with data systems and aggregating different analytical instrument modules into logical analog instrument systems. Founding members of this group include analytical instrument market leaders such as Agilent, Shimadzu, Thermo Fisher Scientific, and Waters. As you can see, we work closely together to develop synergistic specifications for our market. In collaboration with Analytic Jena, we have developed a Let's OPC UA information model for real-time PCR systems as shown in the middle image. Similarly, in collaboration with the company Berthold, we have created a Let's OPC UA information model for a microplate luminescence reader. This device can be seen in the right image. A prototype of this device implementation was exhibited during this year's Future Labs Live show in Basel. All the companies mentioned on this slide are also participating in the ongoing hackathon. This clearly demonstrates the high value and importance of such events. Let's continue with more examples of analytical instruments. The Obsorms plate reader by Bionoy runs its Let's OPC UA server on a tiny and very cost-effective ESP32 S3 microcontroller, utilizing the Open 62451 C programming language stack. This impressively disproves the rumor that powerful hardware resources are needed for running OPC UA servers with complex information models. Furthermore, we have successfully modeled highly specialized instrument types like Eckert and Ziegler's radioisotope detector and their TLC scanner. This highlights the wide applicability and versatility of Let's information modeling concepts across diverse instrument types. Now let's explore some devices used for automated liquid handling and cell processing. The Let's OPC UA integration for Brand's liquid handling system was showcased at this year's Future Labs Live event as well. It powerfully demonstrates the capabilities of the Let's Program Manager as a key feature of the orchestration use case. Next, an implementation of a Let's OPC UA information model for Hamilton's precision liquid handling instrument, which was initiated during the third Let's hackathon. Finally, we have designed a Let's information model for multiplate worktable carbon dioxide incubators, like the Scalar 4-position cell incubator shown in the right picture. Now let's delve into the category of general laboratory equipment. Wireless sensors are becoming increasingly important for sample-centric monitoring along the workflow, and environmental sensing across the whole laboratory. We are delighted that innovative companies like Essentum and Amensio have embraced Let's OPCUA at a very early stage. In almost any laboratory, you will find small-scale mixers, either in single-place or parallel formats. Heidolf and Tumac are two well-known suppliers of such devices, and they plan to provide Let's OPCUA support for their products. The mixers by Tumac have been part of Let's OPCUA showcases from the very beginning of our project. Freezers, incubated shakers and balancers are common workhorses found in most laboratories. Because they are so widely used, we implemented their generic Let's OPCUA models and simulated their behavior in the Let's proof of concept software. This software serves as playground for agile development and testing of concepts during the creation of labs. In the final part of today's presentation, it will play a major role by enabling a virtual laboratory for interaction with collaborative and mobile robots. So stay alert and keep an eye out for exciting demonstrations. And yes, there is much more general laboratory equipment that can be handled by Let's OPCUA. Temperature control of processes is a standard task in laboratories. A typical type of equipment for this task are thermostats, as depicted in the left image. A Let's OPCUA prototype integration for Eulabus immersion thermostat was presented at shows such as this year's Future Labs Live. The Let's proof of concept software provides an elaborated Let's information model and simulation for all types of laboratory centrifuges. One example shown in the center image. Speaking of elaborated Let's OPCUA information models, they are also available for rotary evaporators like the one shown on the right image. Sometimes even we are surprised by the wide variety of laboratory equipment. This happened to me when the company Netsch asked us to create a Let's information model for a dynamic mechanical analyzer, as shown on the left-hand side. To our delight, Let's proved to be capable of handling this specialized equipment as well. Now let's consider two more candidates representing process equipment used in laboratories. Firstly, a process mass spectrometer as shown in the center image, and secondly, single or even parallel bioreactor systems as shown in the picture on the right. Given my personal background as co-founder and CTO of a company pioneering parallel small-scale bioreactor systems for most of my professional career, you can be assured that such equipment can be successfully modeled and implemented with Let's OPCUA as well. The picture would not be complete without introducing some application software capable of supporting Let's OPCUA enabled devices in a plug-and-play fashion. We are delighted that the companies shown on this slide are returning participants of our Let's hackathons, implementing generic Let's OPCUA clients into their applications. Let's start from left to right. LabForward, who hosted our previous Let's hackathon, provides a suite of interworking software packages, including an electronic lab notebook, inventory management, and instrument connectivity. Their connectivity solution, named Lab Operator, seamlessly integrates Let's OPCUA enabled devices in a plug-and-play fashion. For those who saw my last year's presentation, you might recall the demonstration of the Panther Buyer workflow design tool, showcasing the discovery, integration, planning and orchestration of several LADS OPC devices, once again in a plug-and-play fashion. The Laboratory Information Management Solution, ILIMS, by Spectaris, showcases the integration of LADS OPC devices at several events. In many laboratory information integration projects, communication middleware solutions play a crucial role in connecting the different dots to achieve smooth integration. The ZenLab middleware framework by InfoTeam provides built-in support for LADS OPC enabled instruments. I hope that with this overview of LADS enabled devices and application software, you have gained a good impression of the capabilities, suitability and flexibility of LADS OPC as the common language for laboratory and analytical devices. As mentioned earlier, people often wonder about the difficulty of integrating LADS OPC and whether there are any tools and examples available to facilitate the process. In the following slides, I'll walk you through the development workflow for devices, providing insights in how LADS integration takes place during our hackathons and workshops. I will also provide a valuable reference to a LADS server integration workshop available on GitHub under the MIT license. This workshop example can be a helpful resource for those interested in implementing LADS OPC in their projects. Additionally, I'll share an overview of popular tools and tech stacks used in the process. This is the workflow that will guide you from your device and its capabilities all the way to a working LADS OPC integration. Step 1. Begin by gaining a good understanding of your device's capabilities, the targeted use cases, as well as familiarizing yourself with the building blocks provided by LADS OPC. Step 2. Load the LADS OPC node set and its associated OPC node sets such as devices or machinery basics into an OPC modeling tool. OPC node sets are a machine-readable description in a specific XML file format, freely downloadable from OPC Foundation's GitHub. Please note that the LADS node set will be available once it's officially released by the OPC Foundation. Step 3. Model your specific device using the generic building blocks provided by LADS OPC. When done correctly, the result will be a LADS OPC compatible plug-and-play representation of your device's information and capabilities, exported as a node site file from the modeler. Step number 4. Choose an OPC software stack that fits your programming language, toolchain and requirements. Most software stacks allow for direct import of all the OPC node set definitions into your application. With just a few lines of code, you can have a LADS OPC compliant server representing your device up and running. You can then use a generic OPC browser to connect to your server and explore its information model. Now the final step. Binding the pieces of information in the server's information model to the real-world variables and methods of your device's firmware code. This step, which typically follows an iterative cycle of implementing features and testing, might be the most tedious task during the whole development process. To help you get started quickly, we have created a Let's OPC UA server sample project and made it available on GitHub. Besides the source code and the required node set files, you will find the corresponding documentation in the presentation folder of the project. Download the project from GitHub and take your first steps with Let's and OPC UA. It's an excellent resource to begin your integration journey. Here are the tools, tech stack, and resources we utilize in the example project. First, the modeler Xiome is freely available from Siemens after successful registration. For your convenience, the required node set files with the Let's OPC UA information models are already included in the GitHub project. For coding, we utilized Microsoft Visual Studio Code and the TypeScript language with Node.js as the runtime environment. The powerful and feature-rich OPC UA tech stack called Node OPC UA is provided by the company Spectaris. All these resources are available under open licenses on the web. Fourth, for browsing and testing, we typically use the tools Process OPC UA Browser and Unified Automation UA Expert. Both are downloadable after prior registration on the respective company websites. Since we are already discussing tools and tech stacks, let me provide a short overview. Please note that this overview is not exhaustive, so I encourage you to do further research. Here are some OPC UA modeling tools. First, the UA Modeler by Unified Automation, which offers code generation for their different tech stacks. Second, the Xiome application by Siemens, freely available after successful registration. It includes some powerful features like a graphical editor for state machines. We utilized it to build the information models of the Let's OPC UA companion specifications and the workshop. Third, the OPC UA Modeler by Spectaris, the creator of the Node OPC UA tech stack. Instead of providing a graphical user interface, this tool follows a text-based approach. You define your OPC UA information model in YAML formatted text file. Based on this input, the OPC UA Modeler by Spectaris automatically generates the node set files and a documentation in a design that resembles the layout of OPC specification documents. Feel free to explore these options further to find the best fit for your project. When it comes to browsing the information exposed by OPC UA servers, there are several powerful applications to choose from. Whether you prefer a simple text-based browser running in a Linux terminal or a feature-rich solution which various platforms support, you have plenty of options. On this slide, I'd like to present two OPC UA browsers that we commonly use during our hackathons and workshops. First, UA Expert by Unified Automation. This browser is available for download after registration on their website. It runs on both Windows and Linux platforms and offers a wide range of views and tools for inspecting the information and capabilities of any OPC UA server. The commercial version provides additional features such as exporting information models. Second, the OPC UA browser by Process. You can download this browser after registration on their website. It supports Windows, Linux and Mac OS platforms. Its feature set includes not only OPC client-server protocols, but also PubSub protocols with different encodings. These are my personal preferences, but I encourage you to explore other options as well, as there are many great choices available. Find the one that best suits your needs and enhances your OPC browsing experience. Finally, let me introduce you to some of the available OPC tech stacks. I've divided the overview into open source and commercial offerings. In most cases, commercial offerings also include support services. However, some companies provide consultancy and support for open source stacks as well. When exploring open source tech stacks, you'll find implementations for many popular programming languages. For the programming language C, you could utilize the Open 62451 stack. For TypeScript, running on Node.js, there is Node OPC. The OPC Foundation provides a reference implementation for .NET. An open source Java implementation of OPC is Eclipse Milo. A popular tech stack for Python is free OPC in its async.io version. It comes with a huge set of valuable examples. Simply search for their names and you will find them on the web. This is just a short overview. There are stacks for other languages available, including, for example, Rust or Go programming languages. However, it's a good advice to check the supported OPC features as well as the activities of the supporting maintainers and community before choosing a specific open source tech stack for a project. On the other hand, commercial offerings encompass tech stacks for C++, ANSI C, .NET, Java, and even the good old Delphi programming language. While discussing tech stacks for OPC I take the opportunity to dispel an old wives' tale about the supposedly high resource requirements of OPC. During our Let's Hackathon, at least 2 participants successfully implemented their Let's OPC servers on ESP32 as free microcontrollers, utilizing the Open 62451 stack for the C99 programming language. This impressively demonstrates the adaptability and efficiency of OPC technology. Now I'm sure you must be curious about when the Let's OPC companion specification will see the light of day. I can tell you that the specification is currently in the final review phase at the OPC Foundation and will be published this fall. As you can see, the title of the first edition of the standard is Let's Basics. This suggests that additional complementary parts may be developed in the future. For instance, future developments could focus on enabling integration and interaction between laboratory and analytical instruments with collaborative and mobile robots. Another aspect that could be elaborated is referencing device information with semantic definitions, as briefly introduced during my last year's talk. An important prerequisite to enable machine learning and artificial intelligence applications is an efficient and effective manner. Let's now move on to the third part of today's presentation, which offers an exciting outlook on how Let's OPC will serve as the foundation for laboratory automation both today and in the future. You might remember the various laboratory instruments with LEDs information models that I presented a few minutes ago. LEDs OPCA allows for standardized integration of these instruments into automation applications, leading to several benefits including better reproducibility of processes, improved data integrity, increased efficiencies, automation of tedious operations, and more. Last but not least, increased automation frees up valuable human resources, enabling them to focus on higher value tasks. However, upon closer examination, we realized that most equipment was not originally designed for automation integration, but for manual operation by human operators. This presents us with a challenging situation that requires automation of workflows with instruments not initially designed for automation, maintaining high flexibility due to frequent changes in laboratory workflows by ensuring close collaboration with human operators. To meet these demands, the integration of collaborative and mobile robots into laboratory workflows becomes essential. By combining automation with human expertise, we can achieve efficient and effective laboratory operations. When attending trade shows and conventions in the laboratory and analytical domain, when talking to end users, automation with collaborative and mobile robots is at the top of the list, along with connectivity, fair data, and machine learning. Here are some typical examples. A cobot on a lab bench picks up plates and places them in another instrument. Next to him, in the background, a cobot ready to do some liquid handling tasks. A cobot positioning conical vials containing samples in the rotor of a lab centrifuge. A mobile robot that picks up, transports and places labwares with samples, reagents or media throughout the laboratory. As illustrated, supportive robotics solutions are becoming increasingly important for life science and laboratories. When looking at the use cases we've defined, we must consider where we currently stand and what's needed to seamlessly integrate robots. It's great that we know the current state of the instruments, and remote control allows us to perform essential operations like opening a drawer and controlling programs. This is a solid starting point for robot integration, but there's a crucial missing piece: the spatial locations. Robots need precise spatial information to approach and interact with the instruments effectively. This includes the position of instruments on the bench, the location where the samples can be placed into the instruments, and so on. To achieve our vision of integrating instruments with collaborative robots, it's essential to provide this spatial information in a standardized format directly via devices. So let's take the next step and add an additional use case covering robot integration. As illustrated, supportive robotic solutions are becoming increasingly important for life science and laboratories. The Laboratory Automation Plug-and-Play framework, short LAP, initiated by Adam Wolf of Takeda, aims to provide a blueprint for the integration of such robots. It outlines a hierarchical decomposition of the workflows, the corresponding layers of the control architecture and suitable information representations models, including relative spatial locations of all affected elements in the lab. Some illustrative images from one of his publications: a cobot on a laboratory bench transferring plates, a mobile robot performing pick, transport and place throughout the laboratory. To achieve teaching-free robot integration, the lab concept requires defining geometric position for labware handover and other robotic actions for each instrument. In a best-case scenario, this information is directly provided by the instrument or its digital twin. Unleash the power of the OPC ecosystem. The OPC UA companion specification for robotics. Here you go. The OPC UA companion specifications for relative spatial locations. It provides the geometrical definitions of things like an instrument, the relevant attachment points and relationships of those. This is exactly what is needed to create the best case scenario. Just compare the images and you will see how well they match. Implementing this companion specification in a Let's OPC UA enabled instrument turns it into a laboratory automation plug-and-play enabled instrument. A great example of the synergies you can achieve by leveraging the OPC UA ecosystem. To better illustrate how this works, we simply integrated the relative spatial location companion specification into our Let's proof of concept software and added a 3D visualization to build the virtual robotic enabled Let's OPC UA laboratory. The entire scenery, including devices, their process values, set points, states and geometrical positions, are automatically generated and controlled based on the OPC UA information model. Here we are in the virtual Let's OPC UA robotic laboratory. As you can see, the companion specifications for Let's OPC UA and relative spatial locations are placed on the benches. So let's zoom out and look around what we can find in this lab. An assortment of different lab instruments like mixers, centrifuges, work table incubators, plus 2 freezers at the wall in the back. Obviously, the instruments are operated by some invisible ghosts, maybe robots. All of them running, all of them exposing their actual status, including set points and process values, via OPC UA. This information can be viewed on the instrument displays. Within the next minutes, we will focus on the work table incubator. This incubator provides controlled process conditions for cell cultures such as temperature, oxygen concentration, carbon dioxide concentration, and is able to accept up to 4 96 well plates, a very typical labware format. Each 96 well plates will be placed in one of the 4 drawers. A typical operation is picking up a plate once the incubation is complete and its transport to another location for further processing. The drawer opens and exposes the 96 well plate. The current position of the 96 well plate itself and its attachment points for the robot gripper are represented by the green spheres with their colored exits. Each green sphere in this scenario represents a relative spatial location object in the OPC UA information model or one of its attachment points. An invisible robot lifts up the 96 well plate, moves it away, and transports it to another location in the lab. The empty drawer closes and waits for the next plate to be inserted into. After a while, another invisible robot approaches with a new 96 well plate to be incubated. The drawer opens, exposing the position where the plate should be placed. The robot inserts the plate at that exact spot and the drawer closes. How does this look like from an OPCUA point of view? The relative spatial location object representing the 96 well plate is currently linked to the drawer object. Its so-called position frame defines its geometric position in relation to its parent object. The parent object is defined by the base property. Due to the design of the incubator's drawer, the 96 well plate must be turned about 90 degrees about its vertical axis to be placed in the drawer. This is represented by the orientations property B, which is set to 90 degrees. The plate's position relative to the drawer is defined by the properties X, Y, and Z. The robot can derive the attach points where it places its gripper from the corresponding definitions in the attach points list. For example, the X position of the left attachment point is minus 6.3 something centimeters away from the plate's center. I think we can all agree that it's much more convenient for us human beings to see the results of all this data processing in the virtual 3D scenery, rather than looking at the raw data in the information model. But that's how it actually works behind the scenes. While the incubator we have just inspected is one of the few lab devices designed with automation in mind, we will now turn to another typical lab device which is designed for manual operation. A laboratory centrifuge, one of the most common laboratory instruments. Its lid is currently opened, exposing its rotor. The green attachment points define the positions where labware should be placed. Please note that the positions are inclined with respect to the rotor's vertical axis. This is very important information whenever a robot wants to place or pick a labware like a conical vial in the rotor. Whenever stopped, the rotor itself can be oriented in any angle to the centrifuge's cabinet. This is illustrated by the additional attachment points on the outer circumference of the rotor, which is intended to serve as index mark. Looking at the position frame of the rotor object, we learn that the rotor has stopped at an angle of 330 degrees. In the attachment point list, one can find the position of each individual sample position, including its tilt angle. Since the device was not designed with automation in mind, the robot might even have to operate the user interface elements. Some examples. By pressing the lid button in the upper left position of the front panel, the lid is closed. The robot can perform such an operation if the button's position is also defined by a relative spatial location object. By turning the lower right dial, the speed set point for the next run can be defined. Again, the corresponding relative spatial location object is a great help. By pressing the Start-Stop button in the upper right position, the centrifuge run can be started. By leveraging the power of the OPCUA ecosystem, we can achieve the remarkable goal of teaching free laboratory automation plug and play, even with equipment that was not initially designed for automation integration. In the future, laboratory automation can take a big step forward thanks to the OPCUA ecosystem with its diverse companion specifications, covering, among others, laboratory and analytical devices as well as robotics. This opens up exciting possibilities, empowering laboratories with enhanced efficiency, improved workflows, and streamlined operations. The future of automation in the laboratory is within reach, and the OPC UA ecosystem is leading the way. By the way, did I mention that cloud connectivity is an important use case in the laboratory and analytical domain as well? And as you all know, the OPC UA interoperability standard provides a solution for this requirement. Stefan Hoppe visited us during our 4th hackathon, which took place in Berlin at the end of March this year, just 3 weeks ahead of Hanover Fair. During his visit, he asked whether some participants of our hackathon, most of them still very new to the world of OPC UA, wanted to participate in OPC Foundation's UA Cloud Showcase presented live at Hanover Fair. This really resonated and the outcome was great. Some integrated OPC UA PubSub directly into their device software. Others utilized UA Cloud Publisher as edge gateway to push data to the cloud. In the end, we were happy to populate the OEA Cloud dashboard presented at Hanover Fair with live data from our laboratory and analytical devices. And, yes, of course, the Let's OPC UA virtual laboratory that I introduced during today's presentation also uses OPC UA PubSub to publish selected instrument data and status all the way to the cloud. Just watch the sensor signal from the balance as you weigh a series of samples. See the temperature inside the centrifuge compartment rise to ambient temperature as soon as the lid is opened, and so on. OPC UA stands as the unparalleled champion of industrial interoperability standards, boasting a track record of proven security. OPC UA serves as the foundation for digitalization and extends its transformative reach across industries to laboratories. Thank you very much for your interest in Let's OPC UA, the laboratory and analytical device standard. I'm happy to receive your feedback, discuss your comments and answer your questions.